Okay, let's proceed. Now, let's have a look at the process, how we make devices using such a molding compound. First of all, we start with a lead frame in the first step, and to that lead frame we must attach the chip. Nowadays, the most frequent process, also the easiest and the cheapest process to attach a chip is adhesive bonding. So the adhesive is applied, for instance, with some printing process. And after that, we do the chip mounting. That's a so-called pick and place. Process, and then the whole set of lead frames is put into an oven and it is hardened. After the hardening, the lead frames are transferred to the wire bonding machine, and here the individual wire bonds are created on an automatic wire bonding machine. A typical diameter of the wire bonding is 25 micrometer, and in our case here we use gold as a material. After the wire bonding, we go into the molding process, which we will see in more detail. Just to give you an idea how the temperature proceeds here in our case, and we can say the glue curing, for instance, could be around 140 degrees centigrade for maybe 15 minutes or something like that. On the other hand, then it is cooled down. We go into the molding machine. Here, in that case, it was heated to 180 degrees centigrade. It is cooled down, transferred to the post-mold cure oven. Here we keep it for 4 hours. We cool it down slowly. Then we go into electroplating. For instance, the lead frames on the outside, they must be tin plated in order to be solderable. And what is also important is final test and calibration. That is also done in most cases at high temperatures. So such devices, we can see, they have many thermal steps, and of course all elements of such a package must be able to survive such thermal steps. Now let's have a look at the molding reaction. As I said, the thermoset material is in a semi-hardened state. It's a so-called B stage. And when we look at a chemical reaction, typically we can say the higher the temperature is, the faster a reaction goes. And a typical reaction, for instance, in such a molding compound, if we heat it at 100 degrees centigrade, it would go slow. Maybe it would just commence hardening at 10 minutes. And at 1000 minutes, it would be only 50% hardened. 50% hardened means 50% of all possible chemical bonds are formed here. That can be measured, but that would mean the time of hardening would be extremely high. On the other hand, if we go into a process which is at a higher temperature, we can see already having 20 degrees higher, it increases the rate of the reaction almost by a factor of 10, or the hardening times are almost a factor of 10 lower. Again, going to 140 has a similar effect, and at 160 degrees centigrade, the rate of hardening is so high that we can just start here with, let's say, a hardening degree of 50% in that curve. So that hardens very fast. On the other hand, we must say, with such a reaction, we never go to 100% hardening. So there are always bonds which have not been accomplished, which the reaction is not completely finished. And you could imagine that in a way that the non-bonded monomeric molecules are shielded from other non-bonded molecules by surrounding polymeric matrix. And in that way, we cannot achieve complete hardening, but for instance, it takes a very long time going from 70% of hardening to, let's say, 85% hardening. So that means the reaction slows down, and that's a reason why after a few minutes we take it out from the molding machine. So here is molding machine. And here is the post-hardening. So let's think about why not harden in the machine for 4 hours. That's straightforward. Then we would only be able to do one molding shot in the machine every 4 hours. And the molding machine is much more expensive than just a simple oven, which just has a temperature of 180 degrees centigrade. So it's much more efficient to mold in a short process and then to do this post-hardening. It is important to know about such reactions, and such reaction, as we have seen here in this sigmoidal function, can be described by a differential equation. So x is the portion which is hardened, and how it increases with different influences, and one is how much already has been hardened. So if that x is low, that factor 1 here is 1, then we have a high rate, but if we have hardened already 50%, then this is only 0.5, and that means this hardening rate will decrease. That's one effect. So reaction is slowing down over time. And the other effect is what we have seen. We have an exponential increase with temperature. And typically here we have such factors which are proportional to e to the power of some activation energy divided by temperature. So that's a typical Arrhenius equation. And you could say if you have something which involves chemistry, and when you regard temperature dependency, in most cases it is correct to use something like Arrhenius equation in order to describe how the reaction rate increases with temperature. In that way, such sigmoidal function can be modeled, and again it is something like that, and that is something which has not only connection with assembly and packaging, but which is generally important for the understanding in engineering. Okay, another effect in molding is stress development. Here, let's have a look at a very simple model. We have the silicon here, and that silicon is embedded in the molding compound. And now imagine at 180 degrees centigrade, this molding compound is surrounding the silicon, and now the molding compound solidifies. That leads to a certain shrinkage, but that shrinkage also leads to some stress. But most of the stress comes from cooling down from the molding process. So you could say the stress during solidification is limited, but afterwards the molding compound shrinks. And the question is, why does it shrink? So we have seen, for instance, the CTE here is 16, again, ppm per Kelvin. And here, let's say silicon CTE is roughly 3 ppm Kelvin. And both of the materials, they will shrink, but the molding compound will shrink much more, and so we will get some compressive stress on the silicon. And that stress can be estimated. First of all, how can we determine stress? We can say in cooling down, we develop a so-called thermal strain. And that thermal strain is proportional to delta alpha, delta T. So the thermal strain will be the higher, the more we cool, and will be the higher, the larger the difference in CTE between silicon and molding compound. What we also need is some Young's modulus, but here we have a complex system. Of course, you could say the stress in the silicon will be influenced mostly by the Young's modulus of the silicon itself, but on the other hand, also the Young's modulus of the molding compound has an effect. Another question is, of course, how much of the material we have. So if you have more molding compound, it can exert higher forces, and therefore it will also exert higher stresses, or if there's more molding compound and less silicon. So here in our case, we can say we compute an area for the molding compound, and here that's a plastic material, and sorry, that was an error. That should be M, like molding compound. We have an area for the molding compound, and we have an area for the silicon. And if we multiply the area with the Young's modulus, we get something like a stiffness value. And in that way, we could compute the effective Young's modulus of our system, and in that way we can say the stress in the silicon would be proportional to that geometry-dependent factor, which is influenced by the Young's modulus of the molding compound, by the Young's modulus of the silicon, by the area of the molding compound, and on the other side by area times Young's modulus of molding compound and area times Young's modulus of the silicon. Again, that's the effective Young's modulus. Here we have the delta T, and here it's the effective CTE difference. The delta T is always measured against which point? It is either measured against the process temperature, or it is measured from the stress-free temperature. The stress-free temperature is not so easy to determine. In many cases, it can be the process temperature or the hardening temperature, but in some cases, it's just the glass transition temperature. Okay. Stresses are not only so-called global stresses as we have seen them, but we have also local stress effects. So you could say the cause of the problems are global stresses. But always local stresses, local stress concentrations come with global stresses. And so typically local stress is what kills your device. Yeah? Not so much the global stress, which is more uniform, but it's local stresses. For instance, often in such devices we have sharp edges or corners. And as an important engineering rule, we can say always at sharp corners inside materials or at edges, we have stress concentrations. We have stress concentrations here on the silicon. We have stress concentrations here on the lead frame. And of course, what would be very good is when we have rounded edges. But how to make rounded edges in silicon? That's not so easy, and it's very expensive, so it is often avoided. So you could say avoiding the sharpest edges by proper processing, by proper sawing of the silicon, by proper cutting down of the lead frames, then you could already avoid such sharp edges, and you could avoid crack formation in the package and in the chip here. Another phenomenon of such stresses is influences on metals. One thing is if we have something like shear deformation on the chip. So that's mostly in out-of-center positions on the chip. We have some strong shear stress and strain, and that can lead to deformation of metallization. That alone is not bad, but we also have cracks in passivation. And of course, from cracks in passivation, we can have the start of corrosion in the application. Besides this deformation of the metal system on top of the chip, we can also have ball bond fracture. Either the bond is lifted off, or the wire end is shear offed, or rarely the middle of the ball bond is sheared. So in most cases here, the adhesion is the weakest link, and so in that way, the bond is coming off the semiconductor, and that is, of course, an electrical open. Also, sometimes we have the effect that when bonding wires are very close together, they can be just crossed, and come in contact during the bonding process, and that can also lead to short circuits. Okay, here we can see there are quite a number of possibilities why we can mold, but why we do not get proper let's say sound devices from our process. One thing we can do is have some rubber-like particles in the molding compound, so the stress concentrations near the edges and corners are not so bad. There are other tricks we can see. First of all, I said these sharp edges, we have a so-called stamping burr. So that's like a knife. So if you have stamped something and you touch it, you can even cut your finger. It is so sharp. And that burr can be removed by some grinding. And so we get rounder edges here. That is one thing which is important. So we avoid these cracks on the stamping burr. Another effect which is important is when we look at stresses, we must say such an assembly is always unsymmetric. That means it is like a bending structure, and that always means on the convex side we have tensile stress, and on the concave side we have compressive stress. And that would mean we can have stress in the chip surface. By having this depression in the lead frame before we mount the chip, we can control our package in a way that the top side of the chip is in the neutral band of this package. What is the disadvantage? Both the bonding wires and the electrically active structures are in the neutral band, and so that gives them the best protection and the lowest stress. And you could say the most important part of the chip is the surface of the chip, and that is protected by bringing it into the neutral fiber here. Another problem we have often in molding is the adhesion between all the individual parts. In fact, the manufacturers of packages put very much effort into improvement of adhesion between, for instance, lead frame and molding compound, and adhesion is always increased when you have something like dimpled structures. So it is bringing together the two materials, like in a, you could say, like in gear wheels, yeah? So it's mechanical interlocking, and that mechanical interlocking also leads to local decrease of stresses, and that means a crack which can propagate easily here in a flat structure. It cannot so easily propagate here in that way. Yeah? So that means crack propagation is not so easy in such an interlocked interface. And so generally both components, plastic and metal, adhere better. Another trick to improve this interlocking is we have some anchor holes here in our lead frame, or we have some staggered anchor. All of these can be easily produced just in the stamping process of our lead frame. So the lead frame is either etched, if it's a very thin material, just by photolithography and etching, or by some mechanical stamping process. And in both cases, it is quite easy to bring the lead frame into every two-dimensional shape which we desire. Now, let's have a more closer look at the properties of such lead frames. One of my PhD candidates had a very thorough investigation of the influences on stress in Hall sensor packages. And within that investigation, he measured the Young's modulus of very many molding compounds. Due to the collaboration with a certain company, we were not allowed to give the brand name of the material. So LS is low stress. And GR is so-called green molding compound. Green molding compound is one which has different flame retardant substance in it. So you could say in previous time we had mostly brominated resins, and now we have substances which are less environmentally critical, and so these molding compounds are called green. SLS is super low stress. Okay, that should be sufficient. And now let's have a look at the properties. Typically, the temperature range of application would be typically -40 to maybe 180 or so degrees centigrade. But on the other hand, it's often desirable to look at a somewhat larger temperature range, so we do not have to extrapolate our data. So, starting at low temperature, we have a certain Young's modulus, which is relatively high for a plastic material. The reason is that it's mostly a silicon oxide embedded in a little resin here. So, if we lower the temperature, we have more or less a linear behavior, and in all molding compounds it goes maybe down to 100 degrees centigrade. Then, depending on the material, we can say, okay, first of all, we have large differences in between these materials in Young's modulus, and the main factor determining Young's modulus here is the content of silicon oxide. We can see here that material goes down until 150 degrees centigrade. It's more or less a linear decrease, like in most solids and like in most metals and ceramics and glasses and so on. And then we have a very strong decrease of the Young's modulus, at least by a factor of 10, and then we are in a state where the material is rubber-like. Here at the low temperature, it's really solid and brittle. For another material, we could say it starts at higher Young's modulus, it goes down from a lower temperature on, and that transition range here we can see, that is a so-called glass transition. That's a glass transition, and here we have a certain glass transition range. And for instance, the inflection point of that curve could be defined as the glass transition temperature. That's a TG. Okay. So the material becomes soft, or on the other hand, when we cool it from molding, the material becomes hard and stiff. Now let's have a look at the CTE. The CTE, we must first regard how it is measured. To that purpose, we look at the length of a sample over temperature, and we could say, first of all, it increases linearly, so that's a delta L divided by initial length. And then from some point on, which is the glass transition, it increases. Typically, we have a slope here, alpha 1 and alpha 2. And again, here we have the glass transition temperature. As when we measure the slope here, we can see in some materials, even the CTE can go down a little, but when we approach the glass transition temperature, it increases significantly, and that is similar for all materials. So in that case, we could say, simplified, the curve would be something like that. We have a low range, we have a transition range, and we have a high range. So here we have T larger Tg, here we have T is lower than Tg. And for the CTE, we can also say we have two possibilities how to define it, and that is important for when you take CTE values from literature. One is the differential CTE. That is just the slope here. That's a differential. On the other hand, we also have an integral CTE that is also given often. So for instance, people say we start at that temperature and we take the CTE as the integral slope, and that would be the integral CTE. And I can warn you, do not mix this up. Integral and differential CTE. As long as a CTE is not temperature dependent, it doesn't make a difference. So for a metal or for a ceramic, it's not a problem. But in polymers, especially when you exceed the glass transition temperature, there is a big difference. And when you do a simulation, for instance, you can do a large mistake. Yeah? So be aware of this. So, summarizing reactive transfer molded packages, the constituents are typically epoxy Novolac and phenolic Novolac resins. We have a high degree of silicon oxide fillers, which are in the micrometer size. Another material which is added is carbon black, because we know almost all molding compounds are black. The properties of the molding compound, they show a strong dependency on the concentration of the added filler material, and of course also a strong dependency on the type of resin. With an increasing filler content, the Young's modulus rises, and the coefficient of thermal expansion it drops. And the following figures show the relation between these properties, because in our investigation we wanted to know, is there a systematic behavior? And my PhD student, he looked at literature, and there was some guy in Belgium, Mr. van der Velde, and he found that there is a linear dependency between the CTE of such a molding compound and the inverse Young's modulus. So you could say, putting all of these data we had in the previous diagrams together, we could find, with some scatter, they are on a linear line. So that means you cannot have a material which is here. That is impossible. You can only have materials which have a property in that range. You can also not have a material here. So such a material would be worse, because it has a high CTE and at the same time a high Young's modulus. That means inverse Young's modulus is low, Young's modulus is high. So that would mean high stress. That would be low stress. On the other side, also such materials do not exist. We only have materials, let's say, somehow from that range here. Again, some manufacturers are somewhat on the better side, some are on the worse side. But that also shows us we cannot just tailor a material in a way that we can have any combination of CTE and Young's modulus. Next question is, why is it so? Is it a natural law that we cannot have such arbitrary material? And in fact it is, because we have the so-called rules of mixtures. And rules of mixtures are laws where we can estimate how the combination of materials behaves. For instance, when we have a mixture of the epoxy and of the silicon oxide, we have a certain volume content of each. And if this volume content, for instance, of the silicon oxide is, if the volume content of that silicon oxide is higher, that means the CTE of the material will be lower. And in that way, that would be a linear rule of mixture. When we look at the Young's modulus, for instance, we can say we have an inverse rule of mixtures. The Young's modulus of that, the inverse of the Young's modulus of that molding compound, or plastic as we say here, would be, again, let's say that's a molding compound, the portion of silicon oxide divided by the Young's modulus of the silicon oxide plus the portion of the epoxy divided by the Young's modulus. So that here is the volume portion. Okay, in that way, we have seen the rule of mixtures, and in fact, when we go back one side, one of the curves here is the regression curve, that's the blue one. On the other hand, we took the data of the resin and of the silicon oxide, and we computed, based on the rule of mixtures, this other curve, and we can see the model is very similar to the regression, and that is a good indicator that our model described by the rule of mixtures is valid. So in that way, we have a materials modeling, which is very useful for our investigation, and and one thing which is also important is that master curve prevents us from desiring materials which can never exist. Okay, now let's have another look at materials. And that would be the behavior under moisture. And there is a very famous master curve you can find in very many textbooks. And that curve gives us information on the permeability of certain materials against water. And in that diagram, the basis is the permeation of water into a material and through a material is due to diffusion. And now let's have a look at metals. When we have a very thin layer of metal, like for instance 10 to the power of -4 centimeter, that is 1 micrometer, and we have water on one side and something dry on the other side. According to that metal, it takes, according to that model, it takes between 10 and 100 years until the moisture permeates the metal. If on the other side we have something like 1 millimeter here, then we could say, it's 10, 100, it's 10,000 years or so until the water permeates 1 millimeter of such a tight metal. So that is something which is very important. For instance, you can find sometimes some kind of bomb from medieval times. Such a bomb is made of copper, and in the bomb there is some document. For instance, that document says the bishop so-and-so, he gave money for building that church or something like. Then this copper bomb, it is closed by soldering, and it is dug into the cornerstone of such a church, and after 1,000 years you find it and you can read it, and the document is very well preserved because it was kept dry and it could not rot there. And so in that way it shows us we have a very tight enclosure, we have hermeticity. Or often when you have a church tower, you have something like this, and here you have, for instance, a cock here, yeah. And in that here we have often documents. And again, these documents, they are kept hermetic in metals. So the best to seal something is metals. Also the plans to seal nuclear waste is in metals because permeation is very low. On the other hand, if we have ceramics, they can also be quite tight against diffusion. Ceramics sometimes have some defects, so there could be a little permeation, but ceramics are similar to metals, and they prevent mostly permeation of moisture, and they are almost as let's say powerful in making hermetic seals as metals are. Glasses are less good. Moisture diffusion is much faster in glasses than in metals or ceramics, but still glasses can be used for hermetic sealing. Then polymers are worse. The best polymers still are fluorocarbons, like for instance PTFE, Teflon, which are still quite good, but epoxies are worse. So in epoxies we already have diffusion, and when we look at, for instance, 0.1 millimeter, that would mean moisture penetrates epoxies within minutes to hours. Silicones, so silicones rubbers are very frequently used for sealing something. Yeah, if you have something like a gap in your bathroom, you use such silicones. Also, silicones are often used for electronics to embed these. So that's a little annoying, because why do we use silicones when silicones are so bad? So you could say silicones, it's less than a minute until water penetrates 0.1 millimeter, 100 micrometer. They are nothing against moisture, they are like a sieve. So why do we use these? And the reason is silicones are hydrophobic, and if you have liquid water, it just drops off. Yeah? So that means on silicones you will not have standing water, but due to the high surface energy, the water will purl off and it will run away due to gravity. And on the other hand, for instance, if you have electronics going under the dew point, you have precipitation of water, but you have the water not on on metal parts, but you have it on the protective layer of the silicone. And again, here it can pearl off. And in that way, silicones are not protecting against diffusion, but they are just protecting against liquid water running into something. So that's very important. But you should be aware that with polymers you can protect electronics, but you cannot achieve hermeticity. Hermeticity means there is no diffusion. You suppress diffusion, and that cannot be done with silicones. It cannot be done with epoxies or other polymers. The best way to suppress this is metals, ceramics, or sometimes glasses. So in that way, you could say that graph I was showing here is not so precise. It just gives us a guess on how materials behave generally, but it also helps us avoid some very big mistakes. And you must be aware that small molecules like water, but also gases, can penetrate through polymeric materials. Okay, thanks for your attention. Next time we will proceed with protecting polymers against water diffusion.